All right, 11.4, we're going to learn how to add, subtract, and multiply our radicals together. And so what we're really doing is all of Chapter 11 is working towards solving radical equations. And I think that students who go into college algebra from Math 30 actually have a pretty good leg up on just a student who jumps right into college algebra, because you guys get a whole chapter to review all this radical information and how we simplify radicals, how we play around with radicals, which is really helpful because in college algebra you do a lot with radicals in terms of your quadratic formula and having to simplify that. And I know that that's kind of a struggle a lot of times for students who maybe haven't dealt with radicals in a few years, and it just kind of pops up. And in college algebra, we don't have the time or the space in our class to actually allow for that review. And so it ends up being something they have to review on their own. So the fact that you get a whole chapter is kind of a nice segue into that once we get closer to that. So the first thing to note is that in order to do these adding, subtracting radicals, you're going to have something called a like radical. This is very similar to having like terms when you add or subtract just regularly, but with a like radical you have to have the same radicand and the same index. So the radicand is what's underneath. The index is the number that's outside. So I could add or subtract radical 5 and 3 radical 5. I can do that. Both of them have the same radicand, the same thing that's underneath the radical, and they both have the same index of 2. Over here, with radical 5 and the cube root of 5, while the radicand is the same, the index is not. So I have to have both of these things in order to do any adding or subtracting. So when you have like radicals, all you're going to do is you're going to add or subtract the coefficients of those like radicals. The way I usually tell students is kind of pretend like your radical portion, if it's like if you have like radicals, it's kind of like your variable. If you add 5x and 3x, you don't do anything with your x's. All you're doing is adding the 5 and the 3 out front. The same thing is true with your radicals. And so whenever we start adding or subtracting these, we're not going to really mess with anything underneath. We're just going to mess with what's out front. And so I think that's kind of an easy way to draw that association. So we're going to do a couple of them that have the like radicals, and then we're going to see what do we do if they're not like radicals. How do we make them like radicals so that we can do this arithmetic? So the first, it looks like 3 problems are going to have like radicals. The first one is 5 radical 7 plus 3 radical 7. So again, we're going to treat the radical part, since they are like radicals, we're going to treat them like our variable. And so all we're going to do is we're going to add those coefficients that are out front. 3 plus 5 is 8. And then what's under the radical stays the same. Nothing else changes. I'm not going to try and take that 8 inside. I'm not messing with the 7 at all. I just leave it as it is. For B, we have more terms. There's 4 different terms here playing. We have an 11 radical x plus an 8 radical y minus a 5 radical x minus a 12 radical y. So we've got different things going on here. Remember, to have like radicals, they have to have the same index, which all of these do, but then you also have to have the same radicand, which means the same thing underneath. Well, we can't do anything with the x and the y together because they're not the same radicand. But we do have radical x here, and we have radical x here, so we can do that. So we're going to look for the like terms, the like radicals. I have an 11 radical x minus 5 radical x, which will give me a 6 radical x. And then I look for the same thing with my y's. I have an 8 radical y and a minus 12 radical y, giving me a minus 4 radical y. And at this point, I can't go any further. I cannot combine that 6 and that 4 because it's a radical x and a radical y. Those are different. They are not like terms. That's like saying I could take 6x minus 4y. I can't combine those any further because the x and the y are different variables. Does this make sense? Are we tracking? Okay. Do we have questions or clarifications so far on the first two? All right, let's look at our third example. I'm going to turn my paper sideways so that I still have room to write. This one is a 5 plus 3 radical 7 minus, and then in parentheses, I have a 2 minus 11 radical 7. The first thing I'm going to do is I don't want these parentheses because they get confusing, and a lot of times then students are tempted to do multiplication. And so what I'm going to do is I'm going to get rid of those parentheses by simply distributing this negative inside to each of the terms. That's all I'm doing. This first bit stays exactly as it is. I'm not going to do anything with it. It's going to stay as 5 plus 3 radical 7. And then I'm taking the negative into the 2, making it a negative 2. Negative times negative for this 11 radical 7 would give me a plus 11 radical 7. And now I combine my like terms. I have a 5 minus 2. That gives me a 3. And then I have a 3 radical 7 plus an 11 radical 7, giving me a 14 radical 7. I cannot combine that 3 and that 14 because that 3 doesn't have a radical part at all, so it stays separate. Are there any questions or clarifications that need to be made with the like radicals? Very, very similar to doing like terms. And in Math 20, there's a like terms section. I want to say it's 2.1. So if you want to see a correlating video where it's not with radicals, it's just with regular exponents and things like that, you can look at that Math 20 video. All right. So obviously they're not all going to stay that simple. It would be nice, but they're not going to do that. So when they aren't like radicals, what we need to do is we need to simplify the radicals first, and then we will add and subtract like radicals. So basically you're going to be given radicals that don't, as they come straight out of the gate, they're not going to look like they can combine at all. So what we're going to do is we're going to try splitting them apart and seeing if we can actually make them like radicals so that we can do that adding or subtracting that it's asking for. We started doing the splitting and simplifying in 11.3. 11.3 would have radical 32, and we'd split that into radical 16 and radical 2 and simplify it. You're going to have to use that process again today to simplify the radicals, and then hopefully the radicands will be the same, and we can add or subtract them from there. So 11.3 is integral for 11.4. Let's see, we've got 5 radical 24 plus radical 54. So we're going to simplify. So if you needed extra practice with 11.3, 11.4 is actually really nice for that, because you have to use all your 11.3 stuff before you can use 11.4. So our first example, where they are not like radicals out of the gate, we have 5 radical 24 plus radical 54. The indexes are the same, so that's good. But what's underneath our radicals are not the same. So we need to see if by simplifying we can get the same thing under our radical. And so what I need to do is I need to work through and think, okay, what's some perfect squares that might come out of 24 and 54. And it doesn't necessarily mean they're going to have the same things come out or the same things simplify. But I want to pull things out of my radicals so that they are simplified. So remember in 11.3, we had a list of kind of our top squares. Like 1 squared is 1, 2 squared is 4, 3 squared is 9, and then we have 16, 25. And I told you it's a little bit helpful to have that information because then you can identify what's going to simplify out. And so when I look at 5 radical 24, and I'm thinking, what times what gives me 24? There's lots of things. There's 2 and 12, and there's 4 and 6. And right there, I would note, okay, 4 is a perfect square, so I'm probably going to use that. Because that radical 4 is going to simplify. Remember from 11.3 that we write it like this. We can also then write it like this, where we split them completely. It's whichever way you're most comfortable looking at your radicals. If you're okay with one big radical with just a multiplier in between, you can leave it like this when you go to simplify. If you like having them split up like this, you can do that as well. Either way. What is the square root of 4? 2. So this 5 is multiplying against that, so we're going to take 5 times 2, which gives me 10 radical 6. So I have just simplified the 5 radical 24 down to 10 radical 6. So hopefully, when I do my 54, I'm going to have a radicand of 6 so that I'll be able to do my adding. So then I'm going to think, what times what gives me 54? 9 times 6. That will be perfect. Because 9 is a perfect square. And again, if you like to split them, you can split them. You don't have to do this. It's whichever way you prefer. Square root of 9 is 3, and that leaves us with a radical 6. So notice now we have like radicals. So we're going to add the coefficients, giving us 13 radical 6 as our final answer. On all of these answers, you will never be giving decimals. You will always be giving simplified radical form. And the way that you know you're done whenever you come to simplify is look what's underneath. Look at your radicand and say, is there a perfect square in there? Because if there is, you need to keep simplifying. But 6 is not a perfect square. Its factors are 2 and 3. Neither of those are perfect squares. So it is a simplified radical at this point. Questions, comments, clarifications? All right, let's do a little bit bigger one. I'll try and leave those steps up there for this one at least. B, we are going to have 2 radical 45 minus radical 80 plus radical 20. So this one's got 3 different radicals going on. It doesn't really matter how many radicals you have. Your goal is always the same. Let's simplify them down, and then let's do our arithmetic if we are able to. So the first thing that I notice about all of these is these are all factor, like 5 is a factor of all these. 45 is 9 times 5. Well, that's good because 9's a perfect square. Now 80, I'm not quite sure what it is times 5. So I would probably use a calculator just to see, or I would do some mental math or some side math. Remember, you can always do old school math over here on the side of your paper. 5 goes into 8 one time. 5 goes into 36. Ooh, so 16 times 5 is 80. That's perfect because 16 is a perfect square. And then 20 is 4 times 5. So notice each of these is a perfect square times 5, which means we're going to end up with a radical 5 as our like radical, which is really nice for us. This will be 2 times 3, which is 6 radical 5, minus 4 radical 5, plus 2 radical 5. All I did was take the square roots of my perfect squares. I multiplied them by the coefficients if they had one. So radical 9 is 3, so 3 times 2 is 6. The other ones didn't have coefficients. So square root of 6 is 4, square root of 4 is 2. Now I'm just going to add and subtract my coefficients. 6 minus 4 is 2. 2 plus 2 is 4. And I end up with 4 radical 5. How are we doing on that one? That one okay? All right, I'll take your silence that it's going okay. Hopefully that's what it means. Here's C. We've got the square root of x squared minus the square root of x squared y plus x radical y. This one's got no numbers outside of your exponent, but it can still be simplified. Because what's the square root of a square? Yeah, it's just itself. Because remember, we can convert it into the fractions if we wanted to. But this is saying we have x times x, which means the square root of x squared just gives us an x. And then over here, if you want to split it, that also makes this a little bit more noticeable onto what's happening with that middle term. Because the middle term says we have the radical of x squared y. Well, that's the same thing as taking the radical of x squared times the radical of y. You just told me that the square root of x squared is x. So that middle term actually simplifies down into x radical y's. Now what's my final answer going to be? Just x. That's exactly right. Because here we have a negative x radical y, and then here we have a plus x radical y. Well, those are going to go to 0, which just leaves us with an x. Not all of your answers will be, have a radical involved in them. Sometimes you will just get a variable. Sometimes you will just get a whole number or a fraction. So not everything's going to have a radical. All right, we're ready for the big one before we do multiplication. D, we're finally going to do a third root, or a cube root. We have x to the 13th, y squared, minus the cube root of x to the 4th, y to the 8th. So remember from 11.2 that we can go and convert to fractional exponents if we want to, if that's more helpful. You can use those to your liking. If you really like using the fractional exponents, you can do that. The other way you can learn to simplify these variables is asking yourself how many times does the exponent in here under our radicand, is it divisible by the index? Like, can we make x to the 13th divisible by 3 by separating? That's what we did in 11.3. We separated things. So here's what I mean. 13 is not divisible by 3. But I know 12 is divisible by 3, and that's really close to 13. So if I did x to the 12th, that would leave me with just an x left over. X times x to the 12th would get me back up to x to the 13th. That's what I'm trying to do. I'm trying to figure out how to get there. But here, I know that x to the 12th is going to be a perfect cube, and I'm going to be able to take that out. That's my whole process. Again, because if we do it with the fractional exponents, then I'm going to have x to the 12th divided by 3. 12 is divisible by 3. That's going to leave me with x to the 4th. on the outside. And that leaves me with an xy squared inside. So this piece right here is actually this piece if the fractional exponents actually help you. I kind of like the fractional exponents. But I have just simplified that first radical all the way down because x to the first power is not going to come out and y to the second power is not going to come out. So those are going to stay inside. So then I go over to my second radical and I kind of do the same process. Only this time I'm going to get to split up both of my variables because both of them are over the size of the index. So I can turn x to the fourth into x to the third times x. I can turn y to the eighth. What would I turn that into if I was splitting it? Like, what's the closest number to 8 that's divisible by 3 without going over? 6. Yeah. So I can turn y to the 8th into y to the 6th, y squared. So this x to the third being cube rooted will just give me an x. Y to the 6th being cube rooted. Remember, that's the same as y to the 6th divided by 3 because we're doing the cube root. So give me y squared. And that leaves me with the cube root of x y squared. So this part right here becomes that part. Notice by simplifying these, even though these looked way different up here, they actually get down to like radicals. I have the cube root of xy squared. So I can do my arithmetic here. But my rules still apply. So look at this. What I mean by that is I have x to the fourth minus xy squared. Can I do that? Are these like terms? Like, can x to the fourth be combined with this minus xy squared? No, because like terms mean you have the same base with the same exponent. So here's how we pull this all together into one nice term, though. What we're going to do is we're going to say we have x to the fourth minus the xy to the second power, which is our coefficients. And then we put our radical out to the side. Basically, we are factoring out this radical is what we're doing. You're going to do this a lot in college algebra, not necessarily with radicals, but this whole process of where we have two terms, and each of these terms has a like part. We pull that out, and what's left over goes inside parentheses. This is actually factoring by grouping. We've already done that in this class. Chapter 6 with all of our different types of factoring. So really what we just did was we factored by grouping, by pulling out that radical and then putting the coefficients inside. We just listed the coefficients first because it looks better, because those are the coefficients. Coefficients go in front of. This is what you would end up typing in to Pearson. You can't do anything else with it. You don't want to distribute because obviously you just factored it. So redistributing it would not help. And honestly, looking at your homework that I did previously, this one's a tad bit harder than most that you will encounter in here. But this is good because this is the process we will be working with as we start solving the equations using radicals. Questions, comments, clarifications? All right. Adding and subtracting are actually a little bit harder, I think, in general, than multiplying. It's kind of like with fractions. When you add or subtract fractions, you have to have like denominators in order to do that. When you multiply fractions, you don't have to worry about having like denominators. You just get to multiply straight across the top, straight across the bottom, and then simplify. And with radicals, you kind of get an easier way as well. You can multiply everything that's underneath your radical as long as it has the same index. So the only thing you're concerned about when you're multiplying radicals is the index the same? If it is, you can multiply everything underneath, and then you can simplify from there. So a lot of times what we're going to be doing with the multiplication problems is we just really turn it into one big radical and do all the algebra underneath it and pull out anything we can. Now, with this, though, to work, you do have to remember your product rule from way back in Chapter 5, where when you multiply with your exponents, what do you do with them? If they have the same base and you're multiplying, what happens to your exponents? Do you add, subtract, multiply, or divide them? You add them. That's correct. And so we do have to remember that. So you're going to multiply under the radicals with the same index. You'll distribute or FOIL if you need to. And then you always want to make sure that you give a simplified radical at the end. Again, you're simplified whenever you can say that there's no perfect squares underneath. And the way that you know you're simplified in terms of your variables is the powers on your exponents have to be less than your index. So if you're taking the square root, you can't have anything to the third power underneath because 3 is greater than 2. So your exponents have to be less than that index. And then you know they're fully simplified. So we're just going to work problems. Do some examples. We're going to start with radical 6x to the third times radical 8x to the sixth. These have the same index. They're both being square roots. So I like to just turn mine all in to one big radical like this. 6 times 8. We could do 48. I don't know why I stopped in my handwritten notes, but I did. So 6 times 8 is 48. X to the third times x to the sixth is x to the ninth. And for some reason, I stopped there. I think I say this every time I teach this class, and then I'm like, I never go back and actually change my notes like I should. So maybe at this point, like maybe you'd want to do it this way, or maybe you wouldn't. That's why I was looking at my notes thinking, I don't know if I would actually combine those to 48 or not, because 48 is not a perfect square. So actually looking at the 8 and pulling out any perfect squares would have maybe been helpful in the beginning. There's lots of different ways you could do this. In general, I recommend combining and then simplifying. But when it comes to the number part, it might be easier to simplify first. Because what's the perfect square that's going to come out of 48? Remember, my perfect squares are 1, 4, 9, 16. Four will work, right? 4 is going to come out for sure. 4 times what gives me 48? 4 times 12, yep. And then I'm going to go ahead and split up my x's as well. I have x to the ninth. 9 is not divisible by 2, but 8 is. So I'm going to go ahead and split those up. Square root of 4 is 2. Square root of x to the 8 is x to the 4th, leaving me with a 12x underneath. Is that fully simplified? I got one person saying no. Why not? Yeah, you can pull another 4 out. That's exactly right. So this is one of these great times where it's, I made sure to listen to you guys, and we pulled out a 4, and then we have to ask, is there another perfect square living in here at all? And if there is, we still need to pull that out. So 12 is the same thing as 4 times 3. So that means I'm going to have another square root of 4. So square root of 4 is 2. 2 times 2 will give me 4x to the 4th. Square roots of 3x. 3 is a prime number. You can't square root it. X inside is less than the second because we're taking the square root, so that's good. So right here, now we went through quite a few steps. We wouldn't necessarily have to do that. If I saw up here at 48 and thought, oh, that's 3 times 16, Well, square root of 16 is 4, and I could have done it there. There's lots of different ways you can approach these problems. I could also have turned everything into fractional exponents and done it that way. I think that leads to more headaches than anything else, but you do it whichever way makes sense for you. So this would be the final fully simplified answer that you'd want to put into Pearson. Again, I'm not sure why I stopped at this step in my handwritten notes. I probably got distracted and had to answer questions or something and then came back to it. Any questions on this one? All right, let's look at the B. B is a fourth root. So we have fourth root of 4x to the 11th y times the fourth root of 16x to the 6th y to the 22nd. So remember, since they're being multiplied, I can shove them all under one big radical. And then I'm going to choose to leave my numbers separate. The reason why is because if I go to the side, 1 to the 4th is 1. 2 to the 4th is 16. So the fact that I have 4 times 16, the 16 is going to be what I get to pull out. And so I'm not going to combine those together because then I'm just going to re-separate them. But I'll move them to the front. I'll restructure, reorganize. I'll have 16 times 4. And then I have x to the 11th times x to the 6th. The bases are the same. I add my exponents. Same thing with my y's. The fourth root of 16 is 2. And then I'm going to split up my variables so that I have things that are divisible by 4. What is the biggest number that's closest to 17 that's divisible by 4 without going over? 16. So I'm just pulling one x off there. And what about for y to the 23rd? Yeah, to the 20th, which would give me y to the 3rd left over. So 16 divided by 4 will give me x to the 4th. That takes care of that term. Y to the 20th divided by 4 will give me y to the 5th, which takes that term, leaving me with the fourth root of 4xy to the 3rd underneath. Four is not a perfect quadruple, I think is how we would say that. I don't actually know. X to the 1st power and then y to the 3rd power. Both those powers are less than the index, so they are fully simplified at that point. Doing okay? Okay. Let's do C. C is where we're going to distribute. We'll have radical 6x, radical 10x, minus radical 3. This one looks different than the others. We've got a set of parentheses. We've got two different radical terms inside. We've got a radical on the outside. First thing I would look for is if I have a set of parentheses is can I combine the inside radicals at all? And in this case, I cannot. Yes, they have the same index. They do not have the same radicand, and I can't make 10x look like 3 or 3 look like 10x. It's not going to work. So what I'm going to do is I'm going to distribute this radical that's on the outside to both of my terms that are on the inside. So I'm taking radical 6x times radical 10x. Since they have the same index, I can multiply what's underneath, giving me a 60x squared. And then I do the same thing for the next one where I have 6x times 3, giving me an 18x underneath. Well, we need to find some perfect squares maybe that go into 60. 2 squared is 4. 3 squared is 9. 4 squared is 16. 25. 25 is not divisible. 16 is not divisible. 9 is not divisible. What about 4? Think about 60 minutes. Can we cut a clock into 4 pieces? And if so, what is it? 15. Yeah, that's why it's a quarter after, or a quarter tell. That'd be 4 times 15. And I'll just keep working this one radical down until we get it simplified, and then we'll go look at the other one. So square root of 4 is 2, and square root of x squared is x, leaving me with radical 15 underneath. 15 is 5 and 3. Both of those are prime. Neither of those are perfect squares, so it's going to stay as radical 15. Now for radical 18x, 18 is 9 times 2. Square root of 9 is 3, leaving me with a 2x underneath. I can't combine these. They don't have the same radicand underneath. So even though I did use multiplication and I did get to a simplified radical, I'm still having 2 separate radicals. That's totally okay. You still make sure you go down as far as you can. Make sure that everything is as simplified as it can be. And then we leave it in this term. We can't subtract the 2x and the 3 because we don't have any of the like terms going on here. So that is as far as we can take it. So you distribute, then you simplify, and if possible, we can combine further, but we weren't able to do that on this problem. Good-ish. All right, let's look at D. Radical x minus radical y times radical x minus radical y. We're going to sharpen up our FOIL skills. If you need refreshing on distributing and foiling and you don't want to deal with radicals with the mix, go back to chapter 6 when we were doing that. And you can do it with regular numbers and variables. But hopefully we're okay with foiling. Foiling, we're going to do our first terms. So we're going to have radical x, and that'll give me radical x squared. Outer terms, I'll be taking radical x times the negative radical y. So I can do a minus radical xy, because as long as your index is good, which all of our indexes are the same, or indices are the same, then we just multiply underneath the radicals. Middle term, it's going to be the same thing. I'm going to have a minus, and then I have x times y. My last term, I have a negative times a negative, which will give me a positive, and then I'll have radical y squared. Square root of a square just gives you the same base. So I have an x. I have 2 of these radical xy's, so I have a minus 2 radical xy. The square root of y squared is just y. Again, I don't know why I stopped in my notes. Oh, because I wrote it different. Well, this one's different than in the notes, just so you know. But this is a fine problem. This is a fine answer. You can leave it like this, or if you want to bring both of your whole components, the x and the y, out front, and then list your radical last, that's totally fine as well. In my handwritten notes, the problem differs slightly because I don't have a radical on this last y, which is why the solution is different if you go back and reference it. That's just because I just copied it incorrectly as we were doing it. But the process is the same. Foiling is the same. Foiling here is the same as it was in chapter 6. It's just now we have radicals at play. But we can utilize our like terms for adding and subtracting our middle terms. We can still do the simplifying here. All of that still works good. Both of these answers are the same. Both of these answers are correct. I usually advise students, and I usually put all my whole components out front, Because if I go to type this into Pearson, there's nothing wrong with that, but you have to be careful because once you're under the radical in Pearson, if you don't push over, then when you put plus y, it'll just keep extending that radical bar, and then that's a completely different answer, and it will count you wrong. And so typically I encourage students to put the radical portion at the end so that you never actually have to push over and get out from under that radical, and you don't have to worry about any of that. But it is your preference. Just be careful. Look where your cursor is or what is blue. Usually it'll stay highlighted blue while you're under the radical, and then push over to get out from under the radical. Okay, we've got time for one more. So I'm going to skip E. E is the same style of problem, except we're using cube roots. And then I'm going to do F. The reason why I'm choosing to do F is because you will actually see problems like F in college algebra. And so it's a good one to kind of just see now. This one doesn't have any variables at play either, so that's kind of a nice reprieve. You'll have ones like this on your homework. Really, the last 5 are pretty much exactly like F. So again, I can't combine what's in here. I have a whole and I have a radical, so I can't do anything with it. So I'm just going to be foiling. So I take my first, which is 3 times 3, which is 9. I take my outer, which is 3 times a negative radical 6. Now here's where we are going to be careful. I'm not going to get a radical 18. This is a whole number. This is a radical. So I'm going to get a negative 3 radical 6. This one's a little bit different. This is not a radical 3, so I don't multiply what's underneath. I'm multiplying the coefficients. Then I do my inner, which will give me a positive 3 radical 6. And my last would give me a minus, because that's plus minus, radical. Now I would multiply under my radicals. 6 times 6 is 36. Notice my middle 2 terms. Add a plus and a minus of the same thing. Those are going to go to 0. What's the square root of 36? 6. So I'm going to have 9 minus 6, which is 3. You will do this in college algebra for various different styles of problems. Here's a helpful hint. If you are ever foiling and the first term's the same and the last term is the same and the only thing that differs is the sign in between, then that middle term will always end up going to 0. It will always fall out. So you could really just do your first and your last, because really what we're doing is a difference of squares style situation.